So today we'll be talking about an interesting set of numbers called the Fibonacci sequence, aka the Fibonacci numbers. This presentation is by Marisol, Tori, and Lily. Ta-da! Alright, let's get started. Leonardo Pisano, known as Fibonacci, and also Leonardo of Pisa, Leonardo Pisano Bagoyo, Leonardo Fibonacci, Bagoyo, which meant good-for-nothing or traveler back then, but we have no idea what they meant when they were calling Fibonacci that, was also considered a member of the Fibonacci family, was an Italian mathematician that is famous and credited for introducing the Fibonacci numbers into Western mathematics. He was born in 1170 in Pisa, now Italy, and died in 1250, also in Pisa. Fibonacci was raised in North Africa because his father Guglielmo held a diplomatic position there, and he therefore traveled a lot as a child and was exposed to many different types of mathematical systems. He stopped traveling around the year 1200 and began making his own work based on his findings on the mathematical systems across the world and findings of his own. He published the fundamental books on mathematics called Liber Basi, Practica Geometria, Flos, and Liber Guattatore. However, today the most important one is Liber Basi, because that is the book in which Fibonacci explains the Fibonacci numbers. Although the Fibonacci numbers are named after Fibonacci, the Fibonacci sequence appears in ancient Indian mathematics in connection with the Sanskrit language. Within its stress and intonation patterns are the Fibonacci numbers. However, because Fibonacci is the mathematician who spread the ideas of this sequence, it was named after him. The Fibonacci numbers, what are they? Well, they begin out with 1, 1, 3, 5, 8, 13, 21, 34, 55, 89, 144, and so on. And to get this sequence, you start out with 0 and 1, or 1 and 1, and in order to find the next number in the sequence, you simply add the two previous numbers or use a formula to figure it out. Using the number sequence as the area for a square, you can easily see and find the golden spiral, which you can see begins with the drawing of the squares. These squares are made up by the different Fibonacci numbers. And what I mean is that you begin with the square that has a length of 1 by 1, length and width of 1 by 1, 2 by 2, 3 by 3, 5 by 5, 8 by 8, 13 by 13, as you see in this square, 21 by 21. And it goes on and on and on to an infinite amount of squares. And each area of the square is based on the next Fibonacci number. Interestingly, this pattern is present at any time when it comes to the golden spiral. The golden spiral is seen throughout every use of the Fibonacci numbers because one finds it with phi, which is the ratio of each successive pair of numbers in the sequence. Phi is also known as 1.618, and you can use phi to compute the nth number in the Fibonacci series. To get this, you'd use the equation f of n equals phi times n divided by 5 to the 1/2. There are many different theorems and formulas and proofs that coincide with or have direct relation to the Fibonacci sequence, including Pascal's triangle, which is used for probability and statistics. How can we apply the Fibonacci numbers into everyday life? Well, it's seen everywhere throughout nature and plants. Phyllotaxis is the study of the ordered position of leaves on a stem, and leaves are staggered in a spiral for optimum exposure to sunlight. This spiral is the golden spiral. You can also see the Fibonacci numbers in reproductive dynamics, such as with bee physiology, in which one male has one female parent and one female has two parents. So together, both the males and females have a grandparent sequence of 2, 3, 5, 8 grandparents, and so on. Also, if you look at the ratio from males to females in a colony, the ratio is 1.618, or phi. Also, the Fibonacci numbers are seen in sunflowers, which have spiral seed arrangements to maximize the number of seeds that can fit, in flower petals, shells, spiral galaxies, hurricanes, and so on. The Fibonacci numbers have been around for a lot longer than you or I, and will continue to be everywhere. It's a pretty amazing idea that a set of numbers can be present everywhere in nature, if you just take a closer look.